My name is Jacob Bomley, and this is my lab report for Lab 5, Faraday's Law of Physics 2 at Georgia Tech. The key concepts of this lab are Faraday's Law, which states how a change in magnetic flux across an area creates a curly electric field around the perimeter of that area, electric potential, which is when the difference between electric fields at two different points motivates charges to move between the different points, and magnetic fields, which are generated by the motion of charged particles. The purpose of this lab is to analyze a scenario in which a combination of these three concepts have a moving magnet induce a magnetic force against itself. We will have and compare both the physical and computer model of the scenario. In our physical experiment, a strong bar magnet is dropped through a thick tube of aluminum foil. As the magnet falls through the tube, it creates a varying amount of magnetic flux over the horizontal cross-section of the tube, which results in a potential difference around the tube's circumference. Since the aluminum is a conductor, a current flows around the tube, which in turn creates its own magnetic field. This magnetic field creates a force against the falling magnet, so the magnet is slowed and takes longer to fall. This video of the experiment is not slowed down at all, and you can see that the magnet takes nearly a second and a half to fall through the tube. The first part of our code simulates the aluminum tube as a series of thin rings. The dimensions of the whole tube, its length, radius, electrical resistance, and other measurements match those of the aluminum tube used in the physical experiment. In the next part of our code, we simulate the bar magnet using the dipole moment that was calculated in Lab 3 for the magnet, and then also create a function used to calculate the magnetic field of a dipole at a certain location. We then have a function that uses Faraday's law to calculate the rate of change in magnetic flux across a single ring of the tube due to the falling magnet. This value is equal to the potential difference, aka the voltage, around the ring, which can then be divided by the ring's resistance to calculate the current in the loop. We can then use this current to calculate the magnetic force of the ring on the magnet, and add it to the forces of all the other rings to find the net magnetic force on the magnet from the whole tube at any point. We then add the magnetic and gravitational forces on the magnet to get the net force, and then use this net force and Newton's second law to calculate the motion of the magnet over time. We also graph the velocity of the magnet over time. Over 5 trials in the physical experiment, it took an average of 1.4 seconds for the magnet to fall through the tube, and the code model calculated the fall time to be 1.447 seconds. As these times are very similar, we can assume that the model is a very accurate representation of the real-world scenario. This is further backed up by the graph of the magnet's velocity, which increases in the negative direction at first, then levels out for a while before increasing again once the magnet falls out of the tube. When the graph is level, the gravitational and magnetic forces are in balance because the magnetic force increases with the speed of the magnet. But when that force gets too high, the magnet slows back down, reducing the magnetic force. The magnet thus gets stuck at a specific velocity so that there's no net force on it. Finally, for our post-lab questions, we were asked what would happen if the resistivity of the aluminum was reduced to almost zero. If the resistivity of the aluminum was almost zero, then its resistance would be essentially zero. And so for the current across the loop, which is the voltage divided by the resistance, we'd have a value of nearly infinity. Because the current is so high that any sort of motion in the magnet would create an incredibly strong magnetic field in the wire that would repel the magnet, so that would immediately be pushed back up against itself, and so eventually you have that the magnet just floats in place because of the force from the tube is so strong. And if we had holes or slots cut into the tube, then wherever those slots are, there is not a full circuit around the circumference of the tube, so there's no current and thus no magnetic field, and the magnet would fall faster through those sections. This is my lab report for Lab 5, Faraday's Law for Physics 2212. Thank you for your time.